Sound check. Yes, sound check. Video check. Screen check. Start streaming now. Start screaming now. Let's see. Well, I don't know what the delay is like, but if somebody could just type on the chat that the video is active, that would be great. Okay, great. I think we're live. So hello, greetings, chip friends. And it's another beautiful sunny day here in the Bay Area of California. Except there is a very strange mist over the mountains. I wonder why that is. Here I can set up a joke. Is California on fire? Yes, well, who knew? Okay, so this live stream is going to be about reverse engineering a TTL chip from its die image. And you can see here on the screen, in Inkscape, I have a die image of a 5490 chip from Texas Instruments. And if you want to know what that is... Oh, and by the way, the screen, it's kind of high density, so you might want to go to full screen on your video. And I will try to zoom in on things as much as possible. But anyway, so if you want to know what the 5490 is, you can go to my page at project5474.org. And here I have a list of chips and all the decapsulated die images that I've taken. And if we scroll down to 90, we can see that I have two instances of the chip that I've imaged. You can go to the page for Texas Instruments, and here we can see some vital statistics about the chip that I took apart. This is a ceramic chip. I kind of like ceramic chips because they're easy to get at the die. You just apply heat and the top just comes right off. And there's the die image. So annotated die image, that's kind of what we're going after today, along with the schematic. And the other one, which I may or may not get to today, is a 7490 from Stewart-Warner. From 1971. And if we take a look at that, we can see that it looks pretty different. So it'll be interesting to see, if there are any differences in the schematic. There are certainly differences in the layout. What I also have is a link to the data sheet, which goes right to the Internet Archive. And here is the Texas Instruments data book, and you can just, flip through it, and you can see basically what it does. So, all right. So, let's get started. So the first thing is that the majority of stuff here, the majority is going to be NPN transistors. There may be a few diodes, and there's going to be some resistors. And that's pretty much all you're going to find on this chip. So I thought that I would start by just drawing out the sort of structures that we're going to be seeing and that we should look for. So I'm going to bring up my sketch pad here. And let's see. Okay, so here is a chip. And we're going to make an NPN chip. So first we're going to lay down a bunch of N-doped material, and then we're going to lay down a bunch of P-doped material, and then we're going to lay down some more N-doped material. Now, this is extremely simplified. I'm not going to put in, all the details about how you make a chip, but in essence, this is what it looks like. Now, this outer layer of N, that's going to be the collector. The inner layer of P is the base, and the tiny bit of N is the emitter. So there you go. Transistor, emitter, collector. Of course I got that backwards. Collector, base. Okay. The substrate, which is over here, that's the rest of the chip. That's going to be P doped, so that it's the opposite of what your transistors are going to be. So if you look at this, so this is a side view, and if you look at it from the top, it's going to look like this. So here's your chip image, here's your die image. You're going to see an outline of a rectangle. That's going to be your N layer. So there's N. Then you're going to see an inner part, which is P, and then you're going to see another smaller inner part, and that's N. So you can see that the outer one is going to be your collector. The inner one, or the next inner one, is going to be your base, and the small squares inside are going to be the emitter. Now, typically in TTL chips, you're going to see multiple emitter transistors. Really, you can think about this as like if you have a two transistor. Oops, I'm off the screen. If you have a two emitter transistor, you can kind of think of it as two transistors with their collectors connected together and their bases connected together. And in that case, you would actually see another inner square for another emitter. Okay, so this is really the structure that we're going to look for. So the thing that I want you to take away from this is that these are, lacking a better term, concentric squares or nested squares or something like that. Okay, a resistor is just going to look like this, maybe something like this. You're going to see kind of like a wavy line like that. And then there's going to be, a connection over here and a connection over here. So that's one type of resistor. Basically, these resistors are sort of measured in squares, and each square gives you another incremental unit of resistance. And in fact, resistance on chips is measured in ohms per square. And the interesting thing is that squares are kind of unitless, kind of dimensionless, because if you have a square that looks like this, it has the same resistance as a square that looks like this. Simply as long as your contact area is across the entire thing. And the reason for that is that if you lengthen a square, then you're increasing the resistance. But if you widen a square, then you're decreasing the resistance. And of course, if you do both at the same time in proportion, your resistance is going to be the same. And that's why you're going to see something like this instead of like, ohms per meter, or, well, ohms per micrometer, or ohms per, micrometer squared. No, it's just ohms per square. Okay. And I think that's all that I wanted to draw. So let's actually start looking at this chip image and see what we can see. So the first thing that I usually like to do is identify the pads. So you can see the pads, which are these squares on the outside, and they have these funny black lines going off. Those black lines are actually the wires that go to the pins on the actual chip. Now, the pins are going to be ordered in the same ordering as they are, as the pins are on the chip. That's just a physical constraint. So what we typically want to do is find the ground pin. That's usually the easiest to identify. On some chips, now I'm going to zoom in on a pad. Okay, so here are two pads. Now, on some chips, or on many chips, you're going to see a lot of metal. That's what this yellow stuff is on the top. You're going to see a lot of metal that goes around the chip. I guess I should zoom out again. Zoom out. I'm not zooming out. Okay, what happened to my controls? There. Okay. You're going to see a lot of metal going around the chip, and that's typically going to be your ground. So, immediately we can probably say that this pad at the top right is ground. And to verify that, you can look at the pinout and you can start counting and, see if it kind of looks correct. Because if you count and you look at your VCC pad and it also looks like there's a bunch of metal sort of feeding into a lot of things, then you've probably got the right pin ordering. So if we look at this pad, that's pin 10, right? And then, well, let's go around this way. So we have pin 9, that's this pad. Pin 8 is this pad. Pin 8 goes to a thick piece of metal, but it only goes to one thing, so that's good. Pin 7 is down here. Pin 6 would be the lower right. And here is pin 5, which is VCC. And we can see that, it does seem to go off and feed, maybe a bunch of things. It certainly looks different from the other ones. After pin 5, we have a no connect, so there's no pad here. Then we have pin 3, pin 2, pin 1, pin 14, a no connect, pin 12, pin 11, and pin 10. So I think that is correct. So what I'm going to do is I'm going to go to the labels layer, and I'm going to start by... Why aren't these controls working? My controls are just not working today, and I don't know why. Let me unplug a few things. So I'm using a Wacom Cintiq 27-inch drawing tablet. It's a tablet and a screen. Yeah, I've just lost my controls. There we go. Now it's working. So I've got this pen here, so that's kind of cool. And I can move things around. Okay, great. And I've got this other thing. This is, it kind of looks like a remote control, but it's actually, basically you can set up hotkeys. There's like, 4 buttons on one side, 4 buttons on another, 4 buttons in the middle, and then there's a bunch of buttons around here, and then there's this touch ring. And the neat thing is that, first of all, it's wireless. Second of all, it's magnetized, so you can stick it, on either side of the monitor, depending on what handedness you are. And the other neat thing is that you can program whatever hotkeys you want. So, and it's also application dependent. So, you can set up a set of hotkeys for Inkscape, which is what I'm using over here, or GIMP, or, whatever. And you can also get more than one of these if, you run out of hotkeys. So that's kind of neat. Anyway, so I've programmed this so that, oh yeah, and the other neat thing about this, sorry, I'm going all over the place before I actually get to the meat of the video, but anyway, there's raised patterns on these buttons. This one is a dot, this one is a square, and this one is a line, also on the other side, which is kind of neat because what I've done is I've programmed these keys for Inkscape so that the dot is just my cursor. The square will draw a rectangle, and the line enables me to draw lines, which I thought was pretty clever of me. Anyway, so what I was going to do, right, so we've identified which pad is which pin. So I'm just going to go ahead and type, what is that hotkey device called? Well, first of all, unfortunately, it's specific to Wacom, so you have to have a Wacom tablet in order to use it. So if you look on the Wacom website, it'll say what it is. I don't know offhand the model number, but anyway. Yeah, it's kind of unfortunate because I can really see this as a really useful thing, and you know, I'm kind of hoping that somebody makes a third-party one that you can use with, you know, basically you don't have to use it with a monitor. You can use it with whatever you like, and it's just something sitting at the side of your computer, and you can, you know, push the buttons. I'm sure some company must make something like that, but anyway, this is specific to Wacom. Okay, so I'm going to call this ground, and that's really small. I'm going to make that a bit bigger, like, I don't know, 64? Yeah, that looks good, sure. And the, I don't like that font, sans serif is good. Actually, I kind of like using excuse me, Deja Vu sans mono. Okay, so there's ground, and I can also put in pin 11. And again, okay, so instead I should probably just delete this. Let's see, where's my delete key? My delete hotkey. There it is. Copy and paste. Copy, paste. No? Are they not? Oh, maybe it's this. I have copy and paste set up on this thing. There we go. Okay, and then text. So this is pin 11. And what I'm going to do is, first of all, I'm going to zoom out, and just go around the chip and label the pin numbers. So I'm going to copy this and paste this, and this is 12. Oops, this isn't 10. This isn't 11. This is 10. So there's 11. 12 is over here. So copy, paste, and unfortunately, this is a little bit of setup that you have to do. Copy, okay, why? Copy, paste. Usually this works pretty well. Copy, paste. I was pushing the wrong buttons because I'm an idiot. Okay, 12. 13 is no connect. This is going to be 14. And sometimes, unfortunately, you get a double press. So that's kind of what happened there. This is pin 1. Now this is also something interesting that you should know. Pin 1 usually, the pad for pin 1 usually looks different from all other pads. So you can see that these pads are kind of square. Up here, they're kind of square. But this one has, you know, a lot of zigzags, and that's what the chip designers typically do to label pin 1. I think only once I've actually seen somebody put in metal the number 1 next to a pin. Usually, you know, they're square with like a little diagonal cut out of it. But in any case, pin 1 often looks different. So that's another clue that you can use to identify pin 1. Okay, with a chat lag of 1 minute, why is there a wire connected if it's a no connect? There is no wire connected. If you, whoops, hang on. I need to zoom out. Yeah, I'm not doing a very good job zooming out, so. Okay. If you count the number of pads, it's exactly the number of pins that are connected. There are no connects, of course, because, you know, they just wanted to make this a standard package. They only needed 12 pins, and there really isn't a standard 12-pin dip, so they used 14. So obviously they needed to no connect two of them, and in fact, the spaces where there would be pads, but there aren't any, are here between 12 and 14. And where else? Here, I think, between 3 and 5. So there aren't actually wires connecting the no connect pads because there are no pads. All right, let's get back to copy, paste. So this is 2. Paste. So this is 3. Next, this is paste. So this is 5. Press 4 to zoom fit drawing. Yeah. I'm going to try that right now. F4, I think. Well, that didn't work. Maybe it's not 4, maybe it's some other 4, but yeah. Or, you know, maybe I have to just be in cursor land. 4. Ah, that actually worked. Interesting. Thank you very much. Okay, 5. 6. This is kind of interesting. These pads are not square. They've got this diagonal line on them. If there weren't 2 of them, if there were only 1 of these in the entire chip, I would be tempted to call that pin 1, but that didn't happen. So anyway, paste pin 7. Okay, let's go here and paste. This is pin 8, and we're back to pin 9. Okay, and now I'm also going to label the pins with what they're labeled as on the pinout. So 5 is VCC, and let's see, what's 3 and 2? 3 is R0 sub 2. So 3 is R0 sub 2. It's not a very intuitive way of describing what these things do. Usually they're a lot better. You got excited because you spotted a resistor between pin 5 and pin 6. Excitement intensifies. Yeah, there's a resistor right over here. It's not actually between 6. It actually goes to a transistor over here. But, you know, we're getting ahead of ourselves. But well spotted, indeed. Yeah. Okay, pin 1. What is pin 1? Input B. I'm just going to call that B. Paste. B. And paste. And I think this is A. And then 13 is no connect, and 12 is QA. So we have QA and QD. So this is Q, oops, double press. QA. And this one is QD down here. QD. Ground, and then I think we had QB and QA. QB and QA. All right. Okay. Nice. Hotkey 4. All right. So we have all of the pins labeled and numbered. Oops, I missed 6 and 7. Let's do that. So 7 is R9 2, and 6 is R9 1. So R9 2. Copy that, and okay, I guess I didn't copy that. That's okay. R9 sub 1. Okay. So we've labeled all the pin names and pin numbers. Pin 8 is QC, you say? Yeah, I think you're probably correct. I got that wrong. Thank you for checking. QC. All right, so the reason that I did this is that typically with TTL, you're going to see kind of a standard input structure and a standard output structure. So if you can identify the input pins and the output pins early, then you can prevent a lot of mistakes, and you can sort of get your bearings on what you're actually looking at. So for example, we know that QA is an output, so we know that we're going to see the typical TTL output, which is, you know, 1 NPN on the top, 1 NPN on the bottom, and, you know, maybe a diode in the middle going to the pin. So, you know, QA, QB, QC, QD, you're going to see that sort of standard structure. For inputs like clock inputs, inputs A and B, those are pretty obviously clock inputs. Again, you're going to see some sort of a typical thing, some sort of typical structure. And if you go to the data sheet, which I probably have here, if you go to the data sheet, yeah, the Wacom is really expensive, but you can actually get cheaper drawing monitors. I call them drawing monitors. They're actually just touch monitors with a pen. And you can get them for a few hundred US. I tried one. It did actually work. Unfortunately, it didn't come with this, which was really a deal breaker for me. And I wish I had done a little more research into, you know, whether there were third-party separate things like this. But I just said, screw it, I'm in the Bay Area. I may as well just get an expensive Wacom. Wow, that sounded tone deaf. Sorry. Anyway, so let's see. So yeah, so here in the data book, you can see the input and output structures, and that's the sort of thing that you would look for. All right, let's get started at looking for transistors. So this is the first thing that I typically do. So let's see. So we're looking for squares that are concentric or nested, and I think here's one. All right, so here we go. Here is, hopefully you can see my pen moving around, the arrow moving around. So here is an outer square. There we go, outer square. Here is an inner square, here. And here's a more inner square, here. Now you may be asking, what are these other inner squares? Those are actually contacts. So what you need to know is that all this yellow stuff is metal, right? And in order to prevent the metal stuff from touching the semiconductor on the bottom, you've got a layer of glass in between. So you've got metal on the top, and then a layer of glass, and then you've got your semiconductor with, you know, the various doping patterns on the bottom. And the way you make the metal touch the semiconductor is by putting a little hole or a window in the glass. So that's what these squares are here. These are basically contacts between the metal layer and the semiconductor layer underneath. And what I typically like to do is draw that as these black squares. So, you know, and I can just go around and, you know, recognize all of these things as contacts. And, you know, typically what I'll do, you know, is I might just go across the entire chip and look for these contacts. They're really easy to find because they're basically the innermost square of anything, and they're always touching metal. So I'm just going to do a few more. Once you sort of like get started doing once you get started doing one, you're sort of tempted to just go around the entire chip and do them all. And it's really, really hard not to do that right now. So I'm going to force my... here's another one. Here's a big one. Okay. So anyway, this is the transistor that we were looking at what I claim is a transistor. Okay, so those are the contacts. So now what I'm going to do is I'm going to draw a red square for the collector, and that's the outermost square. So I'm going to do this, and I'm going to change the color to this. Okay. Now I'm going to hide that, and then I'm going to draw the next innermost square in blue. So change the color, and then I'm going to hide that layer and change and make another square, and that's going to be green. Now I can unhide it, and now you can see that that's what the transistor looks like. So I chose red because usually the collectors on NPN transistors are connected to positive, and I suppose the base I chose to be blue because it starts with B. I don't know. I'm an idiot. Anyway, and then when I do that, now I can sort of hide that and draw the metal. Now the metal is going to be a line, so I'm just going to start drawing an outline here, and I'm going to color that yellow. And that's kind of a thick outside. Let's see, fill and stroke, stroke paint, stroke style. Definitely don't want that. I want it like smaller. Yeah, that looks good. Sure. Okay, here is another bit of metal. So here's a wire, basically. And this is the real reason why I got a touch or drawing screen. Hang on, let me just grab this selection and grab this selection and do that. Delete this selection and draw it over again. Now that I've got the correct paint settings. So this is the real reason that I got a drawing screen, is because you can draw these shapes really, really quickly. And it really made it a lot more efficient for me to draw these things. Using a mouse, it was just really, really slow and really difficult. So anyway, there is another thing. And now I can unhide everything, and you can see again what a transistor kind of looks like. I think the collector layer could stand a little more opacity, a little less opacity, and maybe the base layer as well. And maybe the emitter layer also. Because I kind of want to see all the layers all at once. Okay, do you think it would be possible to automate some parts of the die reverse engineering using computer vision? Yes. It probably could be done. I did take a very short, brief stab at it using machine learning in order to identify the metal layer and, you know, basically draw out the metal layer. And I had some success, but it was just more efficient for me to, you know, to just go ahead and draw everything out. Yes, I probably could have spent 6 months training a neural network to recognize the metal layer, and then another 6 months training the neural network to recognize, you know, squares, but I just couldn't be bothered. To me, machine learning is awesome, and there's a lot of potential with it, but, you know, I just don't like using the tools. I just find it very onerous. Let's see. What else? So the collector overlaps metal at the top, but it's not connected. That is correct. There is no contact up at the top of here. Also at the bottom, you can see that this wire just sort of goes over that transistor. I don't know why it did. It doesn't look like it had to, but in any case, that's correct. There's no contact, so that's that. All right, so we've identified the collector, and we can see that this wire over here connects to the collector. We can see that, let's see, this wire over here connects to the emitter. That's this green part. And this wire over here connects to the base. So this is a very simple transistor because it's got one collector, one base, and one emitter. And what I'm going to do is I'm going to label it. So label, I'm going to just stick a label in here, and I'm going to call it Q1. And I'm going to make it a little bigger, and I'm going to change again the font. Okay, there we go. So there's Q1, our first transistor. When I get a second transistor, maybe I should start bringing up KiCad and sticking all these transistors down. Okay, so there's Q1. So what I typically like to do is go around the entire chip and look for all of the transistors. So let's see if I can, which is my zoom out key? This one. All right. Let's look for more transistors. Could you explain how to crack open ceramic IC? There is a video. If you look on my channel, there's a video about how to open the ceramic package. I use a torch. Other people just use a hammer and a chisel. I don't like that because you could damage sometimes the chip. What do you do with the chip diagrams once you've worked them out? Once I work them out, I put them on project 5474. There are a lot of chips there that I have die images for, but no schematics, because it takes a long time to reverse engineer one of these chips. Okay, here's an interesting transistor right over here. So it's not exactly a square, but it's square enough. And you can see here is another square, and here is another square inside it. Now, this is a little confusing. There appears to be a square here, which would imply it's a base, but it can't be a base because by definition, an emitter has to be inside a base. So I suspect what we're seeing here is just a collector. And the reason that you see this other square is that typically in order to get really, really good contact between an N-type semiconductor and metal, you put an additional strongly doped N region, it's called an N plus region, in order to get a lot better contact. So I suspect that's what we're seeing here. Probably the same thing over here. Again, the reason that I know that this is not a base and it's not an emitter is because a base would have an emitter inside it, and an emitter would have a base around it, and we don't have that here. We just have the collector around here. So what I think we're seeing right over here is a double collector transistor. And all that really means is that this wire is actually connected to this wire through the collector, which is kind of cool. What makes the transistor is the doping, not the structure. Well, it's actually both. If you go back to the beginning of the video, I drew out what the regions look like. But yeah, the geometric structure is what tells me what the transistor is, only because I know what the geometric structures are actually doped as. You can't actually see the doping. So yeah, that's unfortunate. There are probably some very, very expensive techniques that you can use to see the doping, and as far as I know, that actually involves slicing the chip and then applying a lot of chemicals, and then you can see sort of the doping and how deep it goes. That's just like really, really deep reverse engineering. That's like super professional, ultra $1,000,000 reverse engineering. So no, you can't see the doping. There is one interesting thing, though, that I discovered. Well, I didn't discover it, but I found that I could actually do this on the cheap, is that if you were to remove all of the metal and all of the glass from the chip, and that typically involves just dunking it in hydrofluoric acid. And I typically use, there's a stain remover, and I mentioned this on some other videos, or maybe in my Patreon page. Oh, by the way, if you look on my Patreon page, which you can see down in the doobly-doo, as they call it, you may need to refresh because I added that just before the video. There is a link to my Patreon page. Totally not asking for patronage, but if you want to, that would be great. But I put a bunch of public posts on that page with they're kind of short articles on reverse engineering chips. So you might want to check that out just for the content. Not saying you have to subscribe or anything. Where was I? Right. So I use a stain remover for relatively high hydrofluoric acid concentration. No, the doobly-doo. The doobly-doo, I first learned it from the Vlog Brothers. They called it the doobly-doo, and that was my first exposure to that term. So now I call it the doobly-doo. Anyway, so if you go to my Patreon page, which is in the doobly-doo, there's an article there about hydrofluoric acid and using it to remove the metal layer and the glass layer from a chip. And I found that if you left the chip in hydrofluoric acid, then the p-doped material actually turned darker. So yes, you can actually see some of the doping, but it's limited to the p-doped layer. And the reason that this is, or maybe it's the n-doped. No, it's the p-doped layer. And the reason that this is, that I made this discovery and that it's important, is that if you look at these resistors, now somebody mentioned that they got excited because they saw a resistor. So I'm going to go to that resistor right over here. The squiggly bit is a resistor. Now, resistors on TTL chips are made out of p-doped material, strongly p-doped material, because it has to be relatively conductive, but not too conductive. So there's a certain doping that you use, but it's always a p-doped. And the reason that I know it's p-doped is that you can see this rectangle around it. That's called an n-doped well. It's basically isolation between the p-doped silicon substrate and the p-doped resistor, so that they're not actually connected. There's this N-well in the middle. So you can consider that kind of like an insulator almost. Now, I took apart a chip from Russia. It's a chip that drives Nixie tubes. It's basically a BCD decoder, and then it has 10 outputs for each of the 10 electrodes to a Nixie tube. And I took it apart and I looked at it under a microscope, and I couldn't see a single resistor. There were no resistors to be found anywhere. So basically, you would see this square over here and nothing over here. You would just see these two bits of metal, and they just appeared to end. And I was like, well, there's got to be a resistor in there. I just can't see it. And I discovered that with hydrofluoric acid, the p-doped material actually got stained, so I could see the resistors. So that's kind of cool. Anyway, so there you go. That's the answer to the can you see doped regions? The answer is, well, yes and no. All right, so we had a transistor over here. And anyway, so the reasoning that I use, yeah, it's the, well, not, yeah, 7441, but whatever the Russians called it. The K155, I think, or something like that. I know it had a 5 and a 1 and a K in it. Anyway, okay, so I've explained my reasoning as to what I think each of these squares is. So I'm going to go ahead and draw out this N region. So first, since I'm going to draw out an N region, let me select that. So now I can take the paint settings from there. One thing that annoys me about Inkscape that I really wish I could solve is that each layer should have its own default paint settings for rectangles and lines. And unfortunately, since I switch back and forth so often, that would be really nice, but it doesn't actually happen. So there's the red thing. I'm going to hide that. I'm going to make a base. So I'm going to select the blue region, select the rectangle tool, take the paint settings from that selection, rectangle here, so that's the base, and then the emitter is here. I'm just going to color that green. Okay. All right, and I don't bother drawing out this N plus region. This, I think they call it like an ohmic contact, but it's basically a contact. I don't bother drawing that out. But what I can do is label the transistor. So labels. Let's go ahead and grab Q1, copy and paste, and this is Q2. And later I might actually go around and relabel the transistors. Usually transistors that are close together are actually connected close together, so they're related, and so they should be numerically close together. But anyway, okay, so we're going to go around. Right, so what I was saying is that I usually go around and identify the collector regions first. So I think here's one. Let me zoom out one step. Yeah. Oh, I totally screwed that up. There we go. Okay, so right here is an interesting transistor that I happen to know from experience is kind of a logic type transistor. In that it performs a logical function. So here's the collector on the outside. Let me go ahead and draw that out right now. So collector, draw that out. There's a collector. Oh, there's one right next to it. Okay. There's actually, is this another one? Yeah, this is another one right next to it. And again, you know, just from experience, I know that this is a transistor because I can immediately see the squares and I can see that they're inside, that they're nested. Here's another one. That was easy to spot. And here's another one right next to it. Let's see, anything else? These squiggly bits are resistors. This is actually not a transistor, right over here in the middle. What it actually is a pretty thick resistor. In fact, it may not necessarily be a resistor, or it may be a resistor with such low resistance that it's effectively a jumper. And the reason that it's a jumper is that it has to go, is that, you know, I think the designers needed to make a connection between this wire up here and this wire down here. And unfortunately, there was a wire in between, so they had to make a jumper. This is basically a jumper. So it is a square within a square, but there is no square within a square within a square. And you can see that there's only a contact. You know, let me draw these contacts. Whoops, I'm in the line tool. I wanted to be in the square tool. Here's a contact, and here's a contact. So you can see that there's a contact, and then there's just this square around both contacts. And that basically says that this is just a very low resistance connection. Same thing over here. Contact, contact, very low resistance connection. But this is a collector right here. Line tool. This is a collector. This structure, okay, this is a complex structure. And I think the entire thing is a transistor, but there's this squiggly bit over here. I'll get to this later. There's something that I want to say about squiggly bits and bases, but yeah, here's another resistor-looking thing, but it also kind of looks like a transistor, kind of. So I'll get to that later. Let's see. Squiggly bit, that's a resistor. This, I think, is a transistor. Okay. Let's see what else we can find. Let me zoom out. Okay, so that's what we've got so far. We've got a few transistors found. Let's see if we can go in the upper side and next to this pin over here. Okay, that's not a transistor. But this square probably is. Okay, are there any capacitors inside TTL chips? I think I've maybe seen one. And basically a capacitor kind of looks like a really big piece of metal and then a big piece of like N region or maybe P region underneath it. And the glass is basically forming the insulation between. Right, metal, yeah, exactly, metal over P doped. And yes, they do take up a lot of space, so. TTL was kind of like a dead-end technology. It was great for glue logic, but when you got to, you know, like really high-density designs, like, you know, processors and, you know, other things, they just went with MOS. PMOS in the beginning because they couldn't make NMOS, and then they went to NMOS, and then they went to CMOS. TTL was sort of a side branch that was, again, great for glue logic, but not for much else. Okay. Let's see. I think This is a transistor here, but I'll get to it later because I'm not quite sure. Actually, I am pretty sure. Let's see. Ooh, I'm not sure what I'm looking at here. Oh, yeah. Yeah, okay. Yeah. Sometimes what helps is that because you know that the entire chip is p-doped, and then the next layer down, the next level would be n, and then the next level would be p, and then the next level would be n, is that you can actually start from a region that you absolutely know is p-doped. Like, for example, this region up here is p-doped. And then when you cross a line, well, now you know that you're in an n-doped region. And then when you cross another line, you know you're in a p-doped region. So sometimes if you're not quite sure what, where you are, like, over here, I'm looking at these squares and I'm not quite sure, what level I'm on. You can actually, just sort of say, okay, well, here's P. I just crossed a line, that's N. I just crossed another line, that's P. Now I'm crossing out of that region, so that's N. Now I crossed out of that region, and that's P, and that means that this is my N region right over here. So now that I've got that straightened out, I'll draw this. Draw this. Okay. And here is one. That's something that I've never seen before, is this kind of base region actually going outside of the collector region. That's weird. I don't know what that's all about. Okay, so there's that. Here's one. This is an obvious one. And yes, unfortunately, it gets tedious drawing all of these transistors, but you've got to do the work. Kind of surprised you don't do an edge detect. Yes, I actually could do an edge detect, but I can see these lines pretty easily. With an edge detect, the problem is that the metal just sort of starts to look like, any other doped region. So I guess, I've sort of trained myself to find these. The next chip that I want to do is the 7490, which looks completely different. In fact, can I bring that up? Open recent 7490. Okay, so this is the 7490. It looks more pinkish and colorful, and if you start zooming in, the lines are a little bit more difficult to see. I think the reason for that is that, like, this is a more primitive process, and the glass is thicker, so it's more difficult to see the lines. Especially, okay, like for example here, right over here, this looks like a transistor because it's, it's rectangular, but you can sort of see that there's like all these artifacts around here, and that's not an artifact of the imaging. It's actually an optical artifact. Well, okay, yeah, it's an artifact of the imaging. It's not an artifact of, the compression or anything like that. So it is a lot harder to see the transistors over here. Nevertheless, using knowledge of what transistors should look like geometrically, you can figure it out. So, this is like not something that you want to do really quickly. You really want to know what you're doing. So, looking at that and then looking at this chip, all of a sudden you can see the lines a lot better, can't you? So you don't really need to do edge detect. Okay, collector. Here's one. Collector. Let's see. So this is definitely not a transistor. Well, is it? I think it is. Yeah, actually it is, because there are several layers of squares. Here's another one. So anyway, another important thing to note as I'm doing this is that this is a 5490. It's not a 54L90, it's not a 54S90, it's not a 54LS90. L stands for low power, S stands for Schottky. It's not an ALS, A stands for advanced, or anything else. This is a what they call a standard technology chip. And the standard technology chips are the easiest because the transistors are the largest. There aren't a whole lot of extra components and extra connections going all over the place for optimization for low power, optimization for speed. I've done standard, I've done Schottky, I've done low power Schottky, I've done low power. Those are relatively easy to do. Every time I've looked at an advanced chip, like an ALS, I just can't figure it out because the transistors are really small, and there are diodes mixed in there, and it's just really, really difficult to do. And I'm just not as productive looking at an ALS chip, so I've just sort of given up on ALS chips. Have you tried different lighting colors for different chips? I haven't. Typically, the color is not important so much as the polarization, and you do need a polarized filter for that, which I don't have, so I haven't experimented with polarization. But yes, that's actually a good point. Maybe with polarization, we could see some of these regions a little better. But I can see these regions well enough, so okay. Is there an easy chip you would recommend to have a look at to begin to reverse engineer a chip? Yes. I would say the 7400 chip. The 7400 chip was the very first 7400 series chip. I think followed closely by the 7474, which is a flip-flop. The 7400 is a NAND chip, and it has very little internal logic. In other words, it basically has the input circuitry connected directly to the output circuitry. And when you do that, you get a NAND gate. You can look at Project 5474 and look at the existing 7400 chips that I've done, so you at least have something to compare against. And you could take the images off it and, practice using it. So, yeah, I would definitely suggest the 7400 to start with. If you're more interested in CMOS technology, I don't have a whole lot of CMOS. I do have a few NMOS chips on there. But I've actually found CMOS a lot easier to look at than PMOS and NMOS, simply because they had to do weird tricks in order to get PMOS and NMOS to be fast enough. CMOS is where it's at. So anyway, if you're looking for TTL, definitely a 7400. If you're looking for CMOS, well, they make CMOS versions of like 7400s, right? There's like a 74HC00. I don't know if I've actually put that on Project 5474. Let's take a quick look. Let's go back to 00. So in inventory, it says that I've got a C, that's CMOS, HC, that's CMOS, HCT, that's CMOS compatible with TTL levels. And if we go into the chips that I've done, oh, I actually did do an HC at one point, and an HCT. Let's take a look at the HC. Oops, that's the data sheet. I don't want to look at the data sheet. I want to look at the page so we could see the image. Yeah, you can see that the structure is really, really simple to look at. And if you actually download this and zoom in, you'll see that these complicated structures in the middle, that's actually just a single high power transistor. Basically what you have is you have the drain and the source sort of interdigitated like this. So that's why it looks so complicated. And then, you know, anyway, I'm getting distracted here. Sorry about that. Okay, more transistors. Okay, this, believe it or not, the structure with what looks like a resistor in it is actually a transistor with a resistor in it. The resistor is actually connected to the base. So you can think of this as a transistor whose base is connected to a resistor. There are some implications with respect to integrating a resistor into a transistor, but you know, for our purposes in a schematic, it's just going to look like a resistor connected to the base of a transistor. Same thing over here. You can see that here is the base region. Here is the emitter. Around it is the collector. And this is that, you know, strongly connect. Here's this strongly connected connector thing over here. And then there's this squiggly bit running off of the base. That's actually just a small resistor. Okay, let's see. This is a... This kind of looks like a transistor right over here, and it's awfully big. So here, let's see. Yeah, I don't think this is a transistor. I mean, it might be. I'll come back to that later. This is a transistor. So we've got, here I'll do it from the inside out. So here we have an emitter here. Then we have a base, and you can see that the base has this integral resistor in it. So what I'm going to do is I'm going to draw it. It goes here, 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 and here, and around here. Base. So there's the base, which unfortunately I drew on the emitter layer. It's going to have to be deleted. And switch to the base layer and just do it again. Yes, I could have copied it, but base. And then around it, okay, so you can see this thing over here. Is this an N plus? Now the reason that I'm hesitating is that sometimes they put diodes in here. Now a diode is just a PN region. So in other words, this square over here could be P. Oh wait, yeah, this square could be P, and the outer square could be N, and that could actually be forming a diode. So, well, okay. I'm just going to color this blue. Yeah. I mean, it's kind of big to be, you know, one of those super ohmic contacts. When we get to reverse engineering this particular section, I'll try to explain that a little better. why I think that is a... Yeah, so if I move this out of the way, so you can see that there's a square here, right? But there's another square over here, so why don't I color this also blue? And that's because this square sort of, almost exactly matches the metal above it. So that's why I think that this is one of those ohmic contacts, those super low conductance contacts. This, on the other hand, it's kind of off-center, and it's kind of larger than it seems it needs to be. So that's why I suspect that's actually a different doping region altogether. And again, that's probably going to be really confusing right now, but hopefully, if we actually look at it and stare at it and draw it out, it may actually end up being just a diode. So. All right, so there's a transistor. Same thing here. Let me draw it from the inside out. So here is the emitter. That's green. Here is the base with an integral resistor. Goes around this way and that way, and that's blue. And then the collector, okay, so we've got this other square over here. It's smaller. I'm just going to leave it alone for now. Sometimes you just have to, draw it out, draw it on a schematic, and then realize that there's a component that should be there but isn't. And the way that you know that there's a component that should be there is that you've looked at typical TTL circuits, and, well, this isn't it. So, N emitter. So we'll go and draw that here. Base, that's a square. And collector, that's a square. Oops. Well, okay, that's a square. All right, here's a big, long transistor. Okay, so what I'm going to do here is I'm going to go from the inside out. So I know that this is a transistor because I can see that there are 3 levels of squares. And so the inner squares are going to be emitters. So I will draw those first. Here is one. Here is another one, and unfortunately this area is a little blurry. Here is another one, and here is another one. And let's see, what else have we got? Okay, we have around those, we have the base. So we're going to go to the base layer and draw that. I think that's where it ends. Now you can see that there's this additional square here. Again, maybe it's a diode. I'm gonna sort of do that. Well, see, if I do that, it kind of looks like a connection to a base sort of region. So what I'm going to do is not do that. Delete. And again, I'll get to it later. Let me go to the collector and draw a square around all of these. There's the square, and there it is. Now you can see that this has 4 emitters. So basically this is equivalent to 4 transistors with their bases and collectors connected together. Now I know that a 4 emitter transistor is kind of like a 4 input NAND gate. And this is just something you'll figure out from experience. Okay, so here's another thing. Let's go get some emitters. Here's one. Here is another one. Here is another one. This one is not, and you can kind of tell because the contacts also look different. Here, I'll draw out the contacts. It's a little contact here, a little one here, a little one here, bigger one here, little one here. This is kind of a bigger one here. There's another one. What's that blurry horizontal line I often see going straight through bases? Ah, yes. Okay. Interesting. Okay. So what you're talking about is this kind of fuzzier line. It's not as delineated, but it's clearly there. That is what they call a buried layer. So in order to make transistors a little better, what the collector actually does is it goes deeper and then under the entire structure. So let's go back to the sketch. Delete this. Yeah, so this is kind of an interesting feature. Let's see if I can draw it out properly. So traditionally, I've drawn the P layer here, then there's an N layer here, and a P layer here, and an N layer here. And this is the collector, and this is the base, and this is the emitter. Now, there's also a buried region, and I'm trying to remember how that actually looks. I think it's like this, basically, kind of like this, and it's I think it's an N. I could be wrong on this completely because I very rarely pay attention to the buried layer because it doesn't serve any purpose in the schematic. But it is a physical characteristic of the transistor, and I think the idea is to maybe I should just leave it at that because I obviously don't know what I'm talking about. I do know that it's a buried layer, and I also know that it has no effect on the schematic, so I don't draw it. But yes, well spotted. Okay, where were we? Looking at the emitters of this thing. So here's an emitter. Right, so I was saying that these contacts are smaller, and they're smaller because their regions are smaller. So there's the emitter. Now the base has this funny looking shape, and I've never really figured out whether it mattered or not, but here's the base, and it's got this little neck in the middle, and I've never really figured out whether that's a really teeny tiny resistor. I draw out the schematic, and it doesn't look like, you know, it's important. For all I know, it actually is, but I usually don't draw it as a separate resistor. So let's just go ahead and draw out the base region. There's the base region. And then we've got the collector region. So collector, collector, collector. Okay, so there's our collector. Here, let me go ahead and draw the contacts. For this one. So there's a contact, there's a little one, bigger one, little one, little one, little one. So those are some interesting logic transistors. They're both 4 inputs. All right. All right, let's zoom out and see where we are. Okay. So you can see how much work this actually takes. It looks like, so far I've spent like, you know, an hour just doing this. Of course, I've had, you know, various distractions and side explanations, but, and this is a moderate complexity chip. Let's start from this area. and draw some emitters. Let's draw some contacts. Let's change it up a bit and start drawing some of these contacts. Big contact, little contact, little one. Here's one over here. Here's one over here. Here's a bigger one. Here's a big fat one. Here's a teeny one. Yeah, this is actually an interesting structure right over here. So this is a pin. It's R9 sub 2, which is, I think, an input pin. Yeah, it's an input pin. Now, the input pins of TTL chips typically have a diode that goes to ground, and it's a reverse bias diode, and it looks like this. So here's your typical input in, and typically this is what an input looks like. So there's an input transistor. And rather than talking about why this transistor looks like that, I'll just say that this is an input, and basically, this is sort of like the inverse of the input. The signal right over here is the inverse of the input. Typically what you'll see is a diode, and this is a reverse bias diode, so it's a protection against negative voltages, because if you put a negative voltage on the input, then current is going to flow through that diode. More often than not, destroying the diode, but at least it doesn't destroy the rest of the chips. So, and then of course, because the diode is destroyed, everything else gets destroyed too. So, but anyway, this does protect against small negative voltages and, low current negative connections. So a diode is just a P next to an N, right? And it's basically like this. And it's easy to remember which is which, because P stands for positive, and typically you put the positive voltage on here, and N stands for negative. So, that's how you would normally forward bias a diode. By the way, here's a little trick that I love to talk about. Which is the anode and which is the cathode? I could never remember. But if you look at the symbol for diode, maybe if you turn it around, see how there's a K over here? That K, that's the cathode. And see how there's kind of an A over here? That's the anode. That's my stupid mnemonic. Anyway, I never use the terms cathode and anode anyway, unless I have to. I just use positive and negative. Anyway, what I was getting at is that this is the structure of a diode. Well, you don't have a P butted right up against an N, right? If you have, let me erase this, and PN diode. So if you have, and I'm going to draw a top view now. So here's your chip, and it's p-doped. So there are a few ways that you can make a diode. And typically, the P substrate of the chip is connected to ground. Well, if you're going to make a protective diode that looks like this, oops. Why can't I delete like that? Okay. If you're going to make a protective diode that looks like this, well, the P part should already be connected to ground, right? So all you really need is an N region. So if I put an N region over here, this forms a protective diode. So you know, whatever is connected over here, it now has this sort of structure on it. So that's one way of making a diode specifically for protection, for reverse bias protection. The other way of making a diode, of course, is, well, you really don't have any choice other than to put an N well over here, and then you have a P over here, and then you have another N right over there. Well, that's a diode. And you're like, no, Rob, that's a transistor. And I'm like, yes, everyone, that is a transistor, because a transistor can be considered as two diodes. You can use it as two diodes if you connect it up right. So here are the two diodes. So in fact, a transistor like this, so let's see, this is the collector, this is the base, and this is the emitter. So this is the collector, this is the base, and this is the emitter. Well, if you draw this out as diodes, you get a diode that connects to the collector like this, and you get another diode that gets connected to the emitter. So if you were to connect the base to something positive and the collector to something negative and the emitter to something negative, then your transistor doesn't act as a transistor anymore. It just acts as diodes. And in fact, if you look at the input of a, I'll just pick a 7400 because that's easy to do. Let me draw this transistor here, base, collector, emitter. And that's what it looks like if you treat them as diodes. If you look at the input stage of a 2-input NAND gate or a 7400, it looks like this. One emitter, it's actually a double emitter, right? And there's one input and there's the other input, and then there's a resistor to plus, and then there's this, and it goes off to, I think, just an output, but you know, let's just call it out. And this is input A, and this is input B, and this is VCC, and you've got your usual protective diodes. Well, if you draw this out as diodes, the input transistors of TTL are not treated as transistors. They don't function as transistors. They actually function as diodes. So if you draw this as a diode circuit, here's VCC, here's some resistor, right? And now we've got diodes that go to your inputs, A and B, and then you've got another diode that does this. Well, if you ignore this output diode, this is resistor diode logic. And in fact, the input stage of TTL is just resistor diode logic. So you can see that if I ground B, then current will flow from VCC through the resistor, through the diode, and down to ground. So if this is a 0 and this is a 1, well, I get current that flows this way. That means that current is not going to flow this way, because all the current is being drawn out this way. So, you know, because there's going to be another transistor over here. So essentially this diode is now not being forward biased, right? Because this is now at ground. This is at something like 0.7 volts. And, you know, there's no way that this node over here can go below ground or to be at ground, because there's still this junction over here. So there's no current over here. So basically this thing's off. So you can consider the output a 0. If, on the other hand, both of them are 1, then no current flows through these diodes, and current has to flow through this diode. So that's a 1. That's actually an AND gate, isn't it? Okay. Yeah, I got that wrong. So this is an AND gate, I guess. It's an RDL AND gate. Is that right? Yeah, I think it is, because if either one of these is 0, that pulls this node down to 0. So this is an AND gate. All right, so anyway. Okay, so all that was going. Can you build a very simple computer with diodes? Yes, and the answer is you do need intermediate stages, because every time you have a diode, you lose some voltage. So eventually you lose all your voltage. So you would either have to keep stepping up your supply voltage or put some amplification. And that's really all there is to TTL, to be honest. It's a diode stage in the beginning, followed by, maybe some other logic, which is diode logic, with intermediate stages of amplification, and then you've got an output conditioning stage, and that's all there is to TTL, really. Okay, and you can make unlimited complex combinatorial logic with just diodes. Yeah, you can. But typically, okay. Anyway, what I was going to do is talk about this diode right over here. So I happen to know that this is a protective diode. And I happen to know that, let's see, so this is obviously P right over here. No, this is N. It has to be N. So that means that it is going to be an emitter, I think, or like an emitter. So let me just draw that. The next square has to be P, which means it's a base. And the next square has to be N. So it kind of looks like it would be a transistor, but it isn't. And the reason for that is what? There is a reason, and I forgot. Did I get that wrong? No, I'm pretty sure I got that right. The thing that's worrying me is that I don't see the actual connection to ground. Okay, well, maybe there is a connection to ground somewhere in there, but I will just leave that alone for now. Is it a Zener diode? No, it isn't a Zener diode. You don't really see Zener diodes in TTL logic. You do see Schottky diodes, and Schottky diodes do look different in that they seem to have an extra bit of metal in there, because that's actually a Schottky connection. This is absolutely definitely a protection diode. I know that much. I'm just kind of blanking on how exactly the connections work. We can definitely see that this inner connection right over here, it's got to be an N layer. And again, I'm just not sure where the P layer connects to the substrate or to ground. So I'll come back to that. See, we see the same structure over here. Yeah, so I'll come back to that. Let's do another few resistors. And then maybe what I'll do is, instead of doing the entire, all of the transistors on the chip, maybe I'll just, start drawing out the schematic so that we get a little bit more excitement. Okay. So, oops, wrong color. The chip designer could have messed it up. No. They definitely did not mess it up. And this is a Texas Instruments chip. They did not mess it up. Often you do see, not necessarily in TTL, but in CMOS, you see sort of fake circuits, and that's to prevent reverse engineering, actually. It's to prevent piracy of their chips. So, yeah, sometimes you see fake circuitry, but not in this case. You don't see it in TTL. At least I've never seen it in TTL. Let me draw a few contacts here. Draw a few contacts here. Just quickly drawing some out. There was one over here. Contact. Here's this big contact. By the way, now that we know that this is VCC, here's another contact, here's another contact, another contact. This is VCC, and we know this thing to be a jumper, so we know that this wire up here is also VCC connected. Contact. Very hard not to play the contact game. Okay, emitter. Okay, also what you're talking about are test patterns. Let's zoom out and see if there are any test patterns here. Test patterns. Come on, 4. Oops, I need to be in arrow mode. Why am I not in arrow mode? I don't know. Okay, 4. Okay, hotkeys are not working anymore, so I will manually zoom out like an animal. Here is a test pattern. They're usually at the edges of the chip or in the corner of the chip, and basically all they do is, you know, slap down some doping regions and some metal layers, and to make sure that the registration is correct. So here's an example at the bottom. I guess this is to measure vertical registration of this inner square. Horizontal registration over here with this inner square over here. Could I keep the archive of this live stream public? Yes, all of my live streams are public. Let's see. So here's another complicated bit where I guess they're testing, you know, multiple squares and the metal layer. And anyway, sometimes you can get an idea of the different layers that they use with their test patterns. And you'll see sometimes they just stick some letters down, A, B, C, D, E, F, and each one of those is a different like doping layer or metal layer or something like that. Oh, my hotkey works suddenly. Is there any lettering or numbering around here? Oh, look, they put another test pattern down here in this corner too. I wonder why they did that. It's not like it costs anything more to do that. Anyway, yeah, I don't see any numbering over here. Sometimes they put the number of the chip or a mask revision or something like that. I guess they didn't do that here. So, all right, so what I was doing was going to this transistor over here and drawing it out. So, emitter. There's one. Base goes around it. Collector goes around that. No. Wrong layer. Wrong layer. Delete. Collector. What's the squiggly line right next to the VCC pad? That is a resistor. This thing is a resistor. Hey, I'll draw it. Resistor. I typically color resistors as brown. So here we go. Resistor. Okay. Resistor goes around the contact. It comes around here. Goes around and color it brown. Nope, not brown. That's a resistor. The thing around it, again, is an N well. If you go back to the beginning of the video, I talk about, N wells as isolation. But that's all that is. And I typically do not draw those because, again, they're not reflected in the schematic. And I'm only interested in the schematic. Let me draw out this transistor really quickly. So here is an N emitter. N. There's another one. That's all we have. Base goes around the emitters. Base goes around the emitters, and the collector goes around the base. Base. Okay, let me hide those and just draw these metal bits, because why not? Metal. Metal, metal, metal. Before I do that, let me go to a metal bit that I've already drawn and select it, and then go to the line tool and take the paint from the selection. And now we go back to where I was going, which is here. Great, now I can draw using the same style as before. Metal. Let's draw this pad. Pad, 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 pad. Okay, there's the pad. Here's another one. Ding, 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 ding. And that's probably gonna end up here, 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 here. Bing, bong, boom. Okay, there's that. And then there's this other one here. It goes off to here. Well, what have I gotten myself into? There. Commonly used methods to prevent reverse engineering of chips. Fake circuits, I've mentioned before. Security layers, which are just layers of metal on top. That's just, it's just slathered with metal, and then you can't see anything underneath it, and then you have to very carefully take that metal layer off and hope that you don't damage the metal layer underneath. But for the most part, it's going to be fake circuits. Okay, there is a neat little transistor. Let me draw the VCC metal. Oh yeah, right. And I can't reverse engineer any chip that's older than around the mid-80s, simply because the features are so small that I can't optically resolve them. You can do a lot with X-rays and a lot more with basically MRIs. You can make 3D representations of chips with extremely small features, but we're talking about really, really expensive. And you have to really, really, really be invested in pirating a chip in order to go through that. It's a lot cheaper, if you're in China at least, it's a lot cheaper to just run off a few tens of thousands of more copies of the chip that you were outsourced to make and then sell those. So how do fake circuits prevent reverse engineering? Well, you look at them and they kind of look like they belong in the circuit, so you design your chip exactly the same way, except you make the wrong connections. You make connections that aren't supposed to be there, and then your chip doesn't work. So, okay, so I am going to draw this VCC jumper out exactly like a resistor. So it's going to be just this thing. Now, you know and I know that this is an extremely low resistor, so it's not even going to appear in the schematic. Nevertheless, I put it there because it is a connection. So it is, you know, essentially a wire. So let me go to the metal layer and draw the VCC pad. Okay. And this is probably going to go all the way to the other end of the chip. Well, yes and no. I mean, obviously, if you build the chip and it doesn't work, you're not going to sell it. Well, you might sell it, and, you know, just... I've seen that happen. You sell a chip that doesn't actually work, or that isn't the chip that... that isn't the chip that you bought. Yeah, exactly. Map makers do that. They're called, what kind of streets are they called? Ghost streets or something like that? Streets that don't actually exist. Trap streets. I think they're called trap streets. Okay. Let's zoom out and see how that looks. That looks kind of cool. So it's shaping up to be something. Okay. Let's just go ahead and trace this VCC thing out because it's kind of interesting. This low resistance connection that I was talking about. So there's another wire that goes up here to another low resistance connection. So contacts. Okay. And metal. And here's another contact over here. And we'll draw this thing on the resistor layer, even though it isn't really a well, it kind of is a resistor. So it's brown. That ends up connecting to this bit of metal. Let me just draw this contact over here. And here is another one. So now let me just draw the metal out. So there we go, metal. Metal. Oops, it looks like I missed a contact over here. Could you not omit these fake sections if you come across them while reverse engineering? Well, that's the thing. You have to recognize that they're a fake section. They look like bits of the circuit, except they're not. Right, exactly. They would just copy it without understanding the chip, and then it doesn't work, and you don't know why, because, well, sometimes you may as well just design your own. Contact. Okay. So here's an interesting bit. We can see that there is some sort of resistor over here. connecting this part of VCC to this part. I mean, there's nothing in between except this, you know, this fat layer. So what's going on? It's definitely not part of a transistor. It's a jumper, but it's jumping nothing. So sometimes, as Freud said, a resistor is just a resistor. So that is going to be drawn as a resistor. So now I'm not entirely certain if this is actually VCC or not. So when we go ahead and draw this out as a schematic, you know, we'll just stick the resistor in there and see if it makes sense. And if it does, we'll leave it in. And if it doesn't, we'll remove it. Okay. So kind of assuming that that's VCC, here's a transistor, so I'll just draw that out. I really want to get to, you know, bits of KiCad, because it's already like 1:30. It's already been like 2 hours, and I'm kind of thinking that it's time to actually, instead of drawing things, I'm going to draw this out as a P region, and then draw this as an N region. Nope. Delete. Draw this as an N region here. Here's another transistor. Emitter. Base. Base. Kind of looks like a diode kind of thing. And collector around the lot. Why does that look different? Oh yeah, because it's a line. Oh, my color's wrong. How did that happen? Shift page down is move selection to layer below. Yeah, I could probably do that. But then I'd have to reach over to my keyboard, and I'd much rather program them as a hotkey, which I'm not going to do right now. Okay. Let us, let's zoom out. I just reached over to my keyboard, and I just said that I wasn't going to do that. I'm an idiot. What should I do? Okay. Let me go over to this section with the clock. Oh, yeah, I know what I could do. All right. So I have a graphic that I pulled from the data sheet. Don't need that anymore. Okay, so this is what I pulled. Yeah, I think I did accidentally change opacity on that one. I can go back and fix it later. It's not that important. Maybe you should save. Oh God, I haven't saved. Oh, thank you. Yeah. Okay, so this is the block diagram that I found in the data sheet, and surprisingly, with a lot of these TTL chips, the internal logic that they put, that they draw, very, very closely matches the internal circuitry. So we can see that R9-1 and R9-2 go into a NAND gate. So I thought that what we would do is go to those pins and reverse engineer that NAND gate. So here's R9-1 and R9-2. Okay. Again, I can guarantee you that this square bit over here is a protective diode. I just don't quite get how it works. So I'm just going to draw it in. I just want to be sure we get all the features first. Then we can go and draw out our satisfying schematic. Okay. Let's see. So we've got R9-2 and R9-1 with their protective diodes. Great. They both go to this transistor here. We're up to Q3 now, so I'm just going to call this Q3. Q3. Maybe make that a little smaller. Yeah, that's a good size. So there's Q3 sitting over there. We have a resistor to VCC, so I'm going to call that R1. I think the small thing which you made green square is a low impedance contact. I don't know about that, because if the outside here, message retracted, yeah. Okay. Oops, the message is back. I think the small square, which you made green, is a low impedance contact. Oh, yeah, okay. Well, okay, so the square here, let me just hide all these regions. Okay. So if this square is a low impedance region, then let's ignore it. And that means that this is the anode, which is negative, so it's got to be N. That would mean the outside would be P, and then the outside of that would be N, which we know to be incorrect because that is the substrate. So I don't think that's right. I'm pretty sure that this is an N region. Maybe what's going on is that this is the N region over here, and this is actually the substrate. You know, it's actually it's actually just the substrate. No, because then what is this other square doing around it? I don't know. Okay, so we've got R9-2 and R9-1 going to Q3, going to emitters. We've got the base going through a resistor to VCC, and then we've got the collector going off somewhere. Well, let's do that in KiCad. So I've got KiCad right here. And let me make it a little bigger. Okay, so this is my schematic. So what we need is a dual emitter NPN transistor. Now I have both on project5474.org and here, I have a library, which has, let's see, where's project 5474. So I have a bunch of, just symbols that I made, not high power, but I made specifically dual emitter, quad emitter, quintuple emitter. There's a Schottky transistor with double emitter, triple emitter. There's another triple emitter. There's a PNP. So anyway, I made this double emitter thing, so I can put that here. I'm going to rotate it like that. Okay, now I'm going to grab a resistor and do that. So this I said was Q3, right? Q3. And this was R1, value, not value, U1. Okay. We've got a wire that goes to a pin, R9-1, and another one, that's R9-2. And we've got some wires. And we've got some protective diodes, which I assure you are there. I usually like small diodes. Where's D small? There we go. And then I usually go into editing and make the value invisible. There. And there's a second one here. I guess I'll move its designator. Wrong key. Okay, and now I'll stick a ground here. So ground, sure. And here I know what ground looks like, so I don't need to show the value. Okay, and VCC. And there's that wire just going off somewhere. All right, well, that's an AND gate, as we've discovered. But we're looking for a NAND gate. So let me save this and see where it goes. Okay, so this is the connection that we are going to now trace. It goes off to here, and then it goes off to a transistor. Some of you may know what's coming. So contact, contact, contact. 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 All right. This I'm going to label Q4. So let me go all the way over here and grab my label. Copy. Paste. Q4. Okay, so, and it connects specifically to the base of Q4. So let's pull up KiCad and draw that. I know. Annoying, isn't it? You get so used to doing it one way. All right, so let's pull up a, no, not power, project 5474 NPN. Great. We know it connects to the base, and this is 4. All right, so that's how it looks so far. So hey, we're reverse engineering. Woo! Okay. So we've got the emitter must go somewhere and the collector must go somewhere. Let's see if there's anything easy. Anything easy that we can look at. Well, it's not looking too hopeful. Let me draw the metal. Draw some of these wires in here. This goes off to here. While I'm at it, here's a small section of metal. And let's see, anything else? I think that's good enough. Okay. So, okay, well, here is the okay, so here is the collector of Q4, and it goes to the base of another transistor. So let's just go ahead and label that one too, Q5. Q5. Okay, so there's a base. And this wire down here is actually VCC. If I go across the chip, we know that that's VCC. Oops, there's this tiny little section that I forgot. Metal, and tiny little section here. I think it's probably just going to look like this. Okay, and let me connect both of those. Path, union, okay. Better. Okay, so this bottom bit is VCC. Sometimes what I'll do is I'll just, label it just so I know. But anyway, so we've got Q5. It is a single emitter transistor. Q4's collector connects to the base of Q5, so let's just draw that out right now. So we've got this. Q4's collector goes to the base of Q5. U5. Okay. The base of Q5, that's actually a resistor, and it goes up to plus VCC. And the collector is also connected to plus VCC as well. Plus VCC, just VCC. So let me just copy this and stick it here. And copy this and just put it over here. So that's beginning to look a lot like an inverter. The only thing we would be missing is the ground connection over here. So I guess I should label that resistor. We're on R2. Let me draw that in. So this is now 2. Great. All right, so we're interested in that emitter from Q4. So what is this emitter connected to? Let's take a look. So it goes off here. Looks like another transistor. Let's draw the contacts on that. Contact, here's one, and here is one. Here is another one. Here's another one. That's kind of a weird one. Here's one, and here's one. All right, so we'll call that Q6. Okay. So Q6 has one emitter. So let's go ahead and draw that in. So Q6, paste, it's going to be down here somewhere. UQ6. And what are the connections? So, okay, well, we see that Q5 emitter goes to Q6 collector. So Q5 emitter goes to Q6 collector. Okay. Okay. Q4 emitter goes to the base of Q6. So Q4 emitter goes to the base of Q6. There's also this resistor over here. Let me grab that. Copy, or copy, paste. I'm going to call this one R3. Let me draw the metal on that. Metal, 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 metal. Metal, metal, metal. Metal, 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 metal. Oops. Metal. Mo metal. Mo metal. Did I just connect to ground? I think I'm going to end up drawing ground here. I am going to end up drawing ground. Okay, I know that this is ground because it's on the outside of the chip, so I'm just going to sort of cut it off right there. Yeah, I'm just going to cut it off right here. I can draw the rest of ground later, but in any case, this is ground. So pause button for live streams. Can't you pause it? I thought you could pause it and go back and forth. If not, that's I'm gonna have to have a serious talk with someone, because I definitely don't expect people to pay attention every minute of the live stream. Make this a little smaller. A little smaller than that. Okay. So that's ground right here. All right, so the emitter of what is this, Q6, goes to ground. So the emitter goes to ground, and so does R3. I didn't draw R3. R3 is on the base of Q6. Great. Okay. So copy this. Let me do this. Wire. Okay. Copy, ground, copy, ground. And this we said was R3. Okay, zoom out a bit. All right, this is what we have. Now this sort of structure made out of a resistor, and then a transistor, and then a resistor, and then these two other transistors, that is a typical input conditioner. It's basically an inverter. And this is kind of like a push-pull situation dealio thing. So yeah, so we've got an AND gate followed by an inverter. And have I ever gone to all this effort only to then find documentation or have a company release it? No, actually. I have seen bits of the circuit. So for example, in the data sheet, they're going to have a typical input section and a typical output section, but the stuff in between, I have never actually seen them document that. Well, maybe I have once, but generally no. I hoped you would also reverse some of the hard to see 7490. Right, okay, so okay. I could really quickly switch to that. I mean, you've seen this schematic. We actually have a realistic schematic. We know that it's a NAND gate, and we know that that is exactly what you see in the block diagram. Let's take a look at the other one, and we're going to see if we could see the same structure for R9.1 and R9.2. So let's go ahead and open up this other guy. Okay, here we are. First thing we need to do, find the ground, or find pin 1. Pin 1 would look different from all the other pins. Let's see, I'm going around and, oh, well, this must be ground, right? Because it's connected to this big, thick chunk of metal. Or not, maybe it's this other one. Well, luckily, ground and VCC are separated by 1, 2, 3, 4 pins. 1, 2, 3, 4 pads. So yes, this top one is one of the power pads, and this bottom one is the other power pad. And since we know that the pads follow the same order as the pins, we know that this must be VCC at the top. VCC, pin 6, pin 7, pin 8, pin 9, ground is pin 10. So let's really quickly label this as ground. Ground, let's make it a little bigger than that. Ground. Ground. Okay. Copy that, and here's VCC. All right, so we wanted to look at R9. Here, let me unhide the chat. Couldn't they be in clockwise order? No, because that wouldn't make any physical sense. If you think about it, the chip has pins, right? The pins have to go around the die. So of course it wouldn't make sense to do anything else other than wire the pads directly to the pins. So they have to go in counterclockwise order, exactly as the pins are. Now the numbering of the pins by convention is counterclockwise. So we were looking for R9-1 and R9-2. So we know that that's the next pin over from VCC. So here's R9, what is it? R9-1. So let's just copy that and call this R9-1 and call this R9-2. Okay. So those are the pins we want to take a look at. Well, all right. We can see that. That's funny. Okay, so yeah, so this was made by a company called Stewart-Warner. They briefly got into the microelectronics business after having made like displays or scoreboards or something weird like that. And for some reason in the late 60s, I think, they decided to get into microelectronics and make chips. They didn't last very long, but I've been seeing a lot of Stewart-Warner chips. Anyway, this one was from 1971. So we can see that these two, I'll very quickly draw the metal out because that's easy enough to do. And yes, I typically do make these sounds when I'm alone. Contacts. Okay, here's another contact, another one, another one, another one, another one. This is kind of like those visual tests that the doctor gives you, that the eye doctor gives you. Are you colorblind? Can you see the number through these colored dots? Yeah, I guess if you're colorblind, you're going to have a problem with reverse engineering these things. Here's a big ol' contact. So, big ol' contact. Yeah, because it's a number, because it's a line instead of a rectangle, the opacity is slightly different. So what I'm going to do is select that, select the line tool, grab that from the selection, and then delete this, and then redraw it. So now I have the correct paint settings, or style settings. There we go, that's better. Here's another big contact. So check it out. This is ground right over here. This is the protective diode. So you can see the explicit ground connection, which means that this is an emitter, or rather an N-doped region. So I'm just going to do that. And this is the base. And the square around it is an isolation well. So there's your diode right over there. So, you know, the ground connection is really damn explicit over here. I don't know where the ground connection was on the other one. It's got to be somewhere, but I don't know where it is. I've heard somebody tell me that sometimes the protection diode is actually buried underneath the pad where you can't see it. Well, not only where you can't see it, but also where it doesn't take up space on the die. Wrong layer. P, base. There we go. Well, that's pretty explicit right over there. Okay, so those are the protection diodes. Now, okay, let me draw the metal. You're probably all jumping up and down in your seats because you know what the transistor is and what it's supposed to do. Okay. So this is a little piece of metal that just doesn't do anything. Why is that? Well, because this is probably just a standard transistor, and I'm sure we're going to see this exact shape elsewhere. They just happen to use it, and there was the piece of metal waiting to be connected, and they didn't connect it to anything. They're allowed to do that. I'll draw it in anyway. Let's go ahead and paint settings, metal bit. Okay, another metal. More metal. Here's another bit of metal with a thin piece. Let's just draw that out. Okay. So what I'm hoping is that if you had watched the live stream from the beginning, you saw that I briefly pulled up this chip. And I said, well, because of the colors and everything, it's kind of difficult to see all the lines. I'm hoping that, by watching me work on this other chip over here with very clear lines, you've sort of kind of trained yourself a little bit to see the shapes. And now it should be a lot easier to see what we're looking for here. What's a little more difficult is where are the emitters. Let me hide the metal and zoom in. Okay, can you see this really faint line? It's a faint square. Also, can you see this line going across the metal? That's a clear indication that there was a doping region over here. Now, if we look at the base, you don't see that thin line. Well, okay, you see the base line, but you don't see anything inside there. You see a line around here for the contact, you see a line here for the base, but you don't see this, this other line like here that I'm showing. So even though you can't see well the exact lines, they're not really well defined, they're there. So let's draw them. Green. There's nothing here. Here's a line, so we know that we've got to have something here. Green. Again, we can see a line around here, but it's not inside a base. So that is a low resistance connection to the collector. Around here, interestingly, we don't see any line crossing the metal. So whatever this connection would have been, it probably would have been a base connection, but it's not connected to anything. So let's draw the base. Base, 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 base. It's got a little funny hook here. That's just a small resistor. Base. And let's zoom out. The more different zoom out. Okay, and around the whole thing is a collector. Collector square. Collector square. let's lower the opacity on that. And the bases could stand a little lower opacity also. Oops, I drew it on the wrong layer. No, I drew it on the right layer. Well, okay, whatever. Yeah, I don't know why my bases are looking so purpley. Oh, because their opacity is incorrect. Let me just redraw that really quickly. So I'm going to grab this base, which I like, and then I'm going to choose those paint settings. Whoa. What the hell just happened? And then draw the base. All your bases belong to us now. There we go. Okay. Here's the collector. Now, in the schematic from the other chip, we saw that we had the protective diodes, we had the connections to the emitters. So what we're looking for is a resistor that goes to plus from the base. Here's the base right here. There is a connection up here. Let's just draw it. I already did. And then there is this long line up here that goes up to here, but it also continues and it goes to here, which is VCC. Excellent. So it's no different. It's exactly the same. Save. Interestingly, though, that's interesting. So here's a segment of a resistor, and then there's a connection in the middle of the resistor, and then it continues on to VCC. That's interesting. I wonder why they did that. Well, we're going to put it in the schematic and find out. That's really interesting. Why'd they do that? Okay. Okay, Matthew. Glad you're so excited. So when I've got when I'm reverse engineering multiple chips, that are the same, I kind of like to use the same component designators. So where's the other one? So the transistor for R9, 1 and 2 is Q3. So I'm just going to go ahead and label this Q3. Q3. So that way it's the same thing. Q3, so there's this base resistor. There's actually a lot of different segments. Well, I guess this resistor could be considered a continuance of this resistor. So this is all just one resistor. So I'll just call this resistor. Well, now I don't have an exact correspondence, do I? Hell with it. I'll just call it resistor 1A. I can always do that. I'm allowed. And this is resistor 1B. So in the schematic, basically what I'm saying is that this resistor is actually divided into two. So what I'm going to do is, okay, what just happened? I hate when this happens. Stop it. What? Okay. I'm just going to take this and copy it. copy, and paste. Oh wait, I'm doing it wrong. I'm KiCading wrong. Okay. So now, normally what I would do is I would have a completely different schematic because this is effectively a different chip. But, you know, just for the sakes of comparison, I am going to put them on the same schematic. So let me take this and move it over. Take this VCC and move it up. Copy this resistor and put it here. Move this VCC. Here, let me zoom in a little. Okay, so now this is R1A. Value, no, U, R1A, not RA, R1A, and this is U, R1B. Okay, so that's what we have, and we're going to have something going off here, and something here. Well, let's see where that goes to. So Q3's collector is supposed to go off to a base of another transistor. And well, here's Q3's collector, and there is the base of the other transistor. Let's draw it. An emitter. So here you can actually see the square for the emitter. There's the square. Emitter, base, blue bases, green emitters, red diamonds. Oops. You're stealing me Lucky Charms. Okay. And we call that Q4. Okay, so the collector of Q4 is connected between those two resistors. So let's go ahead and draw that out. So here is Q4. I'll just connect that back up. And the collector is actually going to here. Aha. So I suspect what's happening is that this R2, that's actually this. So what they've done is they've basically just, I guess they could do that. It's kind of an odd decision, but okay. I mean, if that's what they want to do. So I think that this R2 is actually over here. So I'm just going to rename this R2. Rename this R1, and that's what we've got so far. So whereas they had two separate resistors here, here they've got these two resistors over here. I'm not quite sure why they did that. I've never really seen that. So here, name this R1, and this is R2. Okay. Let's see, what time is it? It's 2:10 on the left coast. So should I continue? Well, I guess I don't know. I'll leave it up to you. I mean, obviously some of you are going to want me to continue, and I would continue and continue, but, you know, I'm getting a little bit tired. But, yeah, maybe I'll just stop right over here. We haven't fully reverse engineered the chip, but you can see kind of, you know, how we're getting there. We're getting to that point. Typically what you would do at this point is you would hit the books. There are textbooks out there about TTL design, and you would see what a typical standard TTL circuit would look like. Play some Zork. So, you would see that this kind of circuit is actually what you would find in typical TTL circuitry. Let me actually go ahead and look at TTL circuitry images, and hey, let's look at, let's see where. Yeah, I don't have any recommendations at all for TTL books. Everything that I've done is on the web. Oh, hey, look at this. Here we go. The basic TTL logic circuit is the NAND gate. Well, do some more RISC v5 stuff. I will. So we can see there's that input transistor. Here's that diode. It's called a diode steering circuit because the current either flows this way or it flows this way. And if it flows this way, then you're cutting off this transistor over here. So we've seen this. We've seen this resistor. We've seen this one over here. We've seen this resistor and this resistor. We've seen, well, okay, I mean, we didn't see the totem pole output per se, but at least we did see one transistor on top of another. There's this diode over here that appears on the output circuit. And now I'm kind of wondering if that appears internally. Let's go ahead and really quickly take a look. So what we're looking for is in this circuit, not there, here between Q5 and Q6, is there a diode from the emitter of Q5? Let's look at Q5 for a moment. Q5. Is there a diode between the emitter of Q5 and the collector of Q6? No, doesn't look like it. Okay, well, I thought that, maybe I would find one. Yeah, if this were a diode, then this would actually be a P region. Maybe it is. It could be. It could be a tiny little diode, but I don't know. I'm not convinced. I'm not convinced. Usually, with diodes, they would be explicit. I mean, they would be really clear if they were diodes. So anyway, so it's not there, but that's okay. Well, I guess that's about it. Let's zoom out and see what we've done. So that's kind of cool. I'm probably going to spend the rest of the weekend working on this just so that I can finish it up. When it is finished, you will see it on project5474.org. So please take a look at that website if you're interested. There is a lot more information than just images. There is some reverse engineering tips and techniques and how to actually decap chips. Check that site out. Check out the other videos on my channel and subscribe if you aren't already subscribed, which I cannot believe that you're not. Check out my Patreon page. The link is down in the doobly-doo, one of these things. Not because I'm asking for patrons, although that would be nice, but there are nice articles that I've written about reverse engineering the chips. So I think with that, I am going to end the live stream. You should be able to view the entire live stream, even if you just picked up in the middle, I'm pretty sure. And with that, I think I will say, see you next time. End streaming now. End screaming now.